It's like tomorrow, but minus 5 hours. It's like right now. I guess,
Okay, so for the next talk, Armanda Quintavalle is going to speak about logical operations of quantum LDPC codes. Thank you, Armanda.
So as you can see, I've decided to be honest with the title, and I'm already going to state that I'm going to do only some logical operation or some class of LDPC codes. And by LDPC codes, I always mean codes that encodes more than one logical qubit. So I'm going to go back to the stabilizer code picture, where we have just a polystabilizer code, and we have encoded our information in a code space. But what we want to do, of course, is to run algorithms on it, and we would like to do that in a fault-tolerant way, and that is also efficient, which means both in time and space. And our dream result, of course, will be to obtain fault-tolerant quantum computation with constant overhead. And of course, both in time and space, when by overhead, I mean the ratio, basically the ratio between what your logical circuit will cost you and what a fault-tolerant one actually costs you. And what the threshold theorem tells us is that roughly, if we want to obtain that, we need 3 main ingredients that are LDPC codes with a constant rate and efficient decoding algorithm and the threshold. And what we see in a lot of proposals for architecture is the planar code, but that's not really good enough to obtain a constant overhead. So it's nice because it has local stabilizer in 2D, as efficient decoders, but it doesn't have a constant rate. So for this reason, maybe we should go and look beyond this kind of architectures. So I'm gonna do some more preliminaries, and then I'm gonna review the hypergraph code construction that we have seen both on Monday and Tuesday. And then I'm gonna look at how to do some operation on these codes. Here, there are some references on how to do logical operations on LDPC codes, and I've decided to divide it into these 2 columns. On the left, there are basically proposals that works for any code, no matter, like, without exploiting the structure of the code itself. And on the right, we have construction that exploit the symmetries, the structures, or the properties of the family of codes you are using to ensure that these have enable some logical operations. Basically, either there is some sort of state injection or lattice surgery, or some, I will say, transversal gates way that uses symmetries of the codes. So these are the 2 main or 3 main proposed solutions. And what I'm gonna talk about today is the easier way to get gates on a code, which are transversal gates. So here I said I'm using stabilizer codes, so I'm gonna look at unitary gates. And basically, a gate, first of all, is unitary if it preserves the stabilizer group. So this is the first thing that we should look. And here we have 3 different circuits. And as we can see on the first one, the big boxes that cross more than one line represent entangling operation. And what it means is that if we have, like, a situation like this, as in the first one, when we have divided in that way with a lot of overlap of the entangling operation, what it happens is that depending on how these entangling gates are put into your circuit, a single error could spread in a very bad way. So in the first example, one error could go to all 5 of your qubits. In the next example, you have a in the middle kind of situation where the entangling qubits are partitioned into sets, so you are sure that the spread of the error is limited. And of course, the best possible scenario is the middle one where you only have single qubit polyrotations. So when I say transversal for now on, I'm going to talk about the situation like the last picture. So I'm going to allow for gates that spread errors between sets, disjoint sets of qubits, so that I'm sure that cannot hurt too much the state of the system. Okay, great. So transversal gates are easy. Like you just have to make sure that your operation preserve the code space, and then if you partition your qubit in a smart enough way, you basically have fault tolerance for free. So what is difficult about it, I like to look at this with this example. Let's suppose that you have your code is a box and you are protecting your qubits that are this octahedron, and we have a qubit with multiple logical qubits on the left and one logical qubit on the right. So if doing a logical operation is just painting, like putting a bucket of paint inside the box, what happens is that if you put you have a blue bucket, you're gonna color all the qubits in your box in the same color. And what you really wish for is to have like a magical bucket that is able to color your qubits in different way. But that's, of course, is the main challenge when you have a multi-logical qubit code and you want to do operation in a fault-tolerant way, is that it's probably very difficult to address logical qubit per logical qubit individually. And so this is the first step. Why is it difficult? And the second bad news is that we know that transversal gates are not enough to obtain universal computation. So yeah, they are not enough, and they're also quite difficult. Like they don't allow you to address a qubit individually. So why we should care? Maybe for a few reasons, but at least they are easy to implement. So some people will be maybe able to use them for real. Like they are cheap. Okay, so we're gonna see some gates on hypergraph product code. So let's review. Let's first state why this is a good idea to look at hypergraph product codes. And the idea, again, is the threshold theorem. So basically, they respect the assumption of the threshold theorem. So they give up the locality of the stabilizer to gain in constant rate if you pick like a good family of hypergraph product codes. So for this reason, they are promising, even if they're not good codes in the sense of very good codes, they are a promising route anyway.
What did you mean on your last slide, on the right-hand column? Why is there a cross next to robust and noisy symmetry?
Because you cannot have a single shot setting, you have to repeat the measurement, so you can take that for time.
I see.
What exactly you mean by efficient decoder?
I think polynomial is okay. We would like it to have linear, but yeah. Okay, so I'm going to say that I will have talked about hypergraph product codes and not the planar code, but as we know, the planar code is actually an hypergraph product code, but this is a good news, so we can understand exactly how these codes behave. So we have our grid where qubits are on edges, and we have the face and vertex operator that we maybe remember. And now instead of looking at the grid in this way, I'm going to separate the edges. So we have the vertical ones and the horizontal ones. And instead of drawing edges in these two directions, I'm going to draw circles. So for this 3 times 2, yeah, distance 3, 2, whatever. Planar code, we are going to have these 2 grids, 3 times 3 and 2 times 2. And we're going to look at what is the support of the stabilizers on the grid. And if we take this Z stabilizer, for instance, what we see is that it colors its support on the grid is in this direction. And if we take this parity check matrix, then it's easy to see that actually the first row tells you the direction of the qubit on the left, and the first column tells you how to pick the support on the qubit on the right. And this is true for all stabilizers, right? So this is at position 2, 2. So I will take the second row and the second column, and again, I have the support on the qubit. As for logical operators, we know that a string that percolates the lattice is a logical Z operator for the planar code. And if we translate that into binary land, we see that this is actually only a vector that is in the kernel of this matrix. And this matrix here is actually the only thing you need to build an hypergraph product code. And what you have to remember is that the row and the column span of this matrix is going to define stabilizers, whilst the kernel of this matrix is going to give you the logical operators. So hypergraph product codes are just a recipe that takes 2 parity check matrices and gives you a way to define 2 codes that have stabilizers that commute, so a quantum code. This is the distance scaling in short, as we already know. Okay, so here again is just, this is an Hamming code with 1 more row, but it's just a parity check matrix. And as you can see, what we should remember is that Z stabilizers are going to have rows on the left qubits and columns on the right. The opposite orientation for X. And then we're going to have Z logicals that are vertical on the left and the resultant on the right, and opposite orientation for the X. Okay, so now we can see what kind of logical operation we can do. And the idea is to exploit the fact that the planar code is actually an hypergraph product code. And as such, we know that we can map to a color code picture. And we know that the color code has the Clifford group that is transversal. So we have the Hadamard gate, and with 2 copies, we can also have the C0. And the same idea has been generalized with full transversal gates, can also be used on hyperbolic planar code, and as we're going to see, can also be used on hypergraph product codes. So the main trick to understand how to derive the same folding for hypergraph product codes is to pick a nice basis for your logical Pauli. So here I'm going to take an hypergraph product that is the product of this parity check matrix 2 times. And this is a matrix that is a basis of the kernel of that matrix. So basically gives me the logical operator. But this matrix here has a special form, as you can see, is this star form. I have a bunch of 0 under the pivot, and you can also observe that to the right of each pivot, I only have zeros. So, and this is this is the right basis that help us understand the action of the operators that we're gonna see on the code space. Okay, so let's take this. I told you that each vector in the kernel defines a logical operator, and I'm gonna take the first one. The first one are pivot number 3, so I can define logical operators in this way. So this is the Z, and this is the X support, and since the pivot, I take this column twice, it's 3, I'm gonna put it on 3 and 3. Yeah, like this is the numbering. Or I can select column, the first one, and then the third one, where the pivot are 3 and 6, and I'm gonna define 2 pairs of logical operators. So define like in the obvious way, just translating the support from one of the other. And basically, you know, for every choice of pairs of columns of this matrix, I'm gonna define pairs of logicals that are symmetric in this sense. They are the rotated version of the other. And for each single column, I'm gonna define this one that have this nice, they are the same X and Z support. And this is it. So we can label the logical qubits depending on the position of their pivot. So what I'm gonna have is, of course, like on the right, I should take the kernel of the transpose of the matrix, but yeah, it doesn't matter very much. So we're gonna have, in this case, 17 qubits, logical qubits, and I'm gonna have the special one that have the pivot that is on the diagonal, and then I'm gonna have pairs that are paired above and below. Okay, so now let's remind ourselves what the Hadamard gate does. The Hadamard swaps X and Z. Here I've just put for reference the stabilizer of our code. And let's see what happens if we apply an Hadamard to the code. It maps, you know, vertical things blue in orange one, but this is not what we want for a Z stabilizer. So what we do is we fold and these 2 grids of qubit across the diagonal, and we swap qubits that are paired. And what we obtain is that, you know, we have now the correct direction for the stabilizers. Okay, so if we do Hadamard, fold, and swap, we preserve the stabilizers, which is the first ingredient that we need to ensure that an operator is illogical. And let's see what it does on the logical level. So let's take this logical Z here. If we do Hadamard and swap, then it just goes to the logical Z for itself, whilst on the qubit that were paired, so for instance, this one highlighted, the one that have the pivot that is not on the diagonal, they're gonna swap. So the logical action is to an Hadamard on all the qubits that have pivot on the diagonal, and Hadamard and swap between pair of qubits. Okay, so the other logical gate that the color code suggests us is an S gate. Here is a bit different, but so what we do is we apply an S gate on the diagonal qubit on the left and an S dagger gate on the diagonal qubit on the right, and then we do CZ between paired qubits. And the symmetry that we exploit to see that this is in fact a logical operator is that here I just draw a Z stabilizer and the next stabilizer, and what happens is that each stabilizers, either if 2 stabilizers cross on a diagonal qubit, then they cross on 2. Okay, so this is, and this holds for all the stabilizers. So this means that both X and Z stabilizers, if they support as in them a qubit that is on the diagonal, then it also has another one, which means that if I apply a S gate on one end and an S dagger weight on the other, for all the stabilizer, this phase is going to be canceled. And this is like the symmetry thread you exploit. Like you have to find something that the stabilizers have in common and the logical do not. And with this trick is easy to see that the logical action of this gate is going to be CZ between pair of paired qubit and S dagger on the diagonal, depending on the sector the qubits are in. Okay, so this is, we have already seen that we do have the problem of addressing individual qubits. So maybe it's not great, but maybe this method can help us in another setting. So not only the planar code is an hypergraph product code, but the toric code as well. And the toric code is different because it's symmetric, meaning that the span of disparity check matrix and the transpose is the same. So what it happens is that we have two grids, the left and the right, that have the same size, and also, you know, is being that the span on one side on the column and on the row is the same. Also, the stabilizers are going to be like completely symmetric. So what we can do is we can exploit the same trick and pair qubits in the left and in the right sectors like that. And what we're going to have in this picture is, you know, like the qubit at the front are going to have stabilizers, Z stabilizer that span the columns, and the qubit on the back, Z stabilizer that span the rows, and it's the same. So, of course, we can use the same operation that we have defined, but pairing qubit in the front and in the back will define the same logical operations, basically, as we have seen before. Okay, so what can we do about that is, you know, maybe a way where we can exploit this construction is to help parallelization. So what I mean by this is that we know that if we want to perform a CZ between these two logical qubits in the front and in the back, what we can do is that performing a CZ between each qubit in the support. So as you can see, I paired the yellow one, and the yellow one is going to touch all of them. And we can understand, exploiting this basis, how to do that in a parallel way. So what I mean is that, you know, in time step one, we can, in a parallel way, do all the logical CZ here, and so on in step 2 and 3. So of course, this scales with the distance because we need to touch each qubit in the logical support. And we are also leaving the code space, but we could use some peaceable fault tolerance, like in the do correction in between gates, and understand, you know, and help us to pack as many logical operations as possible in each time step. So here, for instance, I've paired, you know, all the things in pink. Like we can do all this CZ between pair of qubits of the same color in one time step, and this will be like 1, 2, 3, 4 logical CZ with 4 time step of cycles. Okay, so this was all I had to say. I think that the main problem is how to address individual logical qubits, even if I also believe that it is not all there. Maybe, like as Oscar was saying, one should. I don't think so. I think we could do better. One should use codes with one logical qubit to do operation, and use other codes just for storage. And of course, we would like to go higher up in the Clifford hierarchy. But what I think it would be different, like there is a complementary problem, or maybe two, I've not touched on, which is how to build a code family that has a certain gates property, which is a completely different question with respect to the one given a code family that behaves in a way that I like for some reason. How do I do logic on that? And then there is also the problem, if you give me a code and I know nothing about it, how can I understand which gates it has, like natively in a cheap way? And there is no reference. I've been working with Mark Webster on that, and for instance, we found like some algorithm to find transversal gates on arbitrary CSS codes, and like exploiting the symmetries and knowing, having an intuition of what is preserved, what should be preserved by an operation could help you adding constraints to the algorithm and having a better like runtime. That's it.
Okay, so you showed several constructions. Can you summarize? I can do H parallel on a block of symmetric hypergraph.
Yeah.
So H on all logical qubits at the same time.
And swap. H and swap, yes.
H and swap. And then
Yeah.
secondly, you can do Control Z
On some pairs.
on some pairs.
And that's stagger on some others.
But the cost is that the time it takes is linear with the distance of the code.
No, okay, CZ, like doing CZ across all pairs of qubits, of logical qubits that I've said, that's transversal. What I like in the last slide here, I was just saying, this method like is a bit poor because I do operation on all logical qubits at a time, which is maybe not what you want to do. So what you really want to do is to do CZ between like the black qubit and the pink one. And to do that, you can use this round robin circuit, and this is costly. But at least this construction can help you pack more operation, like do that in the time steps with also other logical qubits.
With this like folding, when you have surface code, you kind of showed like folding, there's like a nice circuit that takes that to color code. Is there some version of color code for these more general hypergraph products where there's some symmetry between the two things you take the product of?
Like you're saying whether I can refine a color code via this folding?
Yeah, like is there some circuit you can do to take it to a new code that's like local on the pentagraph and treats X, Y, and Z kind of equivalently?
I don't know. I think at the end of the day, like they are exactly the same thing. Even when we, like even before with those, like the operation that were easy, they say in the dynamic automorphism codes are the same. That are transversal in the color code and are the same that you can obtain on hypergraph product codes. So it looks like you could be able to.
Did you think about transversal gates that you could do between two different blocks of two different copies of the same hypergraph product?
No, but because I think like that's another picture, and like what can you gain?
Well, I mean, if you could address like a subset of logical qubits and
Like you could do,
because then you
Like-
can, then you have lots of ways to move qubits around.
you will have, it would be doing logical computation with an auxiliary code, or you would like to use both.
I mean, I don't know. I think I could do a lot if I could do that.
For these feasible fault tolerant constructions, do you have a sense of, in terms of their actual like circular performance or threshold, how they would behave?
The problem is that you change stabilizers, and it can go very badly. So I think case by case, you have to find a way to not completely destroy your code. Like it could be as big as the code distance in principle. So.
Hi, thank you for the very nice talk. Could you remind me, like, what were the assumptions you needed on the classical codes for the techniques to work? Was it?
Okay, so for the first one, you just need to take the same code twice. So you have an hypergraph pilot code that has two grids that are square. And for the second one, you need a parity check matrix that is symmetric. It doesn't need to be symmetric. It's just important that the span of the column and the span of the row is the same. Yeah, so
But-
symmetric.
I was just curious. So while developing these techniques, did you see things happen which would kind of indicate to you that if you put more assumptions on the classical codes, what more interesting gates can you get on a subset of hypergraph product codes?
Yeah, I think you can play with that.
I was just curious. I think there are at least some classical coding people here, so I thought maybe that could. I mean, if we can distill out just a classical coding problem from this, I think that would open up the opportunity for more people to contribute. Thanks.
So, okay, so I can imagine a hypothetical situation when you have a code and you can have multiple fault symmetries. And then it would have like multiple versions of the Hadamard as well, right? So the more symmetries you find in the code, the more gates of symmetry you get. So could there be a constructive way to come up with hypergraph protocols with multiple fault symmetries in opposed to one?
So like maybe you could exploit the parity check, the classical parity check matrix,
Yeah.
or also you can do higher up in dimension. Like this is for 2D, but like for
Nikos fault construction gates, if you look at like two-dimensional hyperbolic circuits, there will be multiple faults. And I think that will give multiple different gates rates. So in principle, there could be a condition put in for the classical code.
code. Yeah, you're right. Yeah.
Faults, right? And that will give us higher like symmetric gates. So there could be like a hierarchy of more codes like yours, that like with more symmetry that you put in by hand, right? And there will have more gates, maybe even more visibility. Right?
Yeah.
But that's not code.
Yeah.
You haven't
I haven't.
got it.
Last question. Okay, let's thank Armanda. And we are going to start 15 minutes